Today I will be talking about example-based photometric stereo with non-local reflectances. A bit of background about example-based photometric stereo is that we use some sort of reference object with known normals in order to reconstruct another sort of object, such as this water bottle. The key advantages to this method are there's very little calibration involved. It can support any sort of BRDF, so long as the reference and target objects have a similar BRDF. And we can also do this for any sort of lighting, such as point lights or also area lights, which not all photometric stereo approaches allow for. Furthermore, this algorithm is pretty straightforward and easy to understand. Now, one of the key concepts that allows for this algorithm to work is orientation consistency, which basically means that regions with similar surface orientations will have similar reflectance behavior under the same lighting. Now, some key assumptions that allow for this property to hold are orthographic. The camera should be orthographic. The BRDF of one material is similar to that of the other, and non-local reflectances and transmittances, such as interreflectance, are ignored. However, this third assumption is what we'll be breaking and testing today to see how the results may differ. Now, moving on to my setup. For my setup, I spray painted 3 objects with a relatively specular spray paint. A plastic sphere, which I used as my reference object, a water bottle, which is the object that broke that third assumption, and a peanut butter jar, which held to all 3 orientation consistency assumptions. I also placed my camera about 3 feet back and had the focal length zoomed all the way in to mimic an orthographic camera. And then after capturing all of my images, the first step to do was to extract my sphere. And so what I did for that is I cropped out a region of the image with just my sphere and then applied some thresholding to create this binary mask, and then tried to maximize the amount of white pixels over the circle area. And then after capturing my sphere, or my circle, I mapped, I used a k-nearest neighbors algorithm to map pixels from my target image onto pixels within the sphere, in the sphere image. And then once I got the corresponding pixel coordinates on the sphere, I used those xy coordinates to solve for z by solving for the implicit sphere equation, and then assign the normal consisting of those xyz back to that pixel in the target image. And then, as you can see here, my results for the peanut butter jar came out well. However, the water bottle seems to be lacking a lot of detail in the parts that were mostly shadowed during my captured photos. So yeah. And after I retrieved these normals, I integrated them using my code from assignment 5 in a similar manner, where I enforced integrability using singular value decomposition to solve for some matrix Q that I could multiply my pseudonormals with in order to get some integrable normals. And after that, I integrated via Poisson integration. And as you can see here, my normals for the water bottle came out relatively the same, whereas my normals for my peanut butter jar actually lost a lot of detail. And so this kind of translated over to my results, where my peanut butter jar was really flat. However, it did preserve some of the details, such as the ridges in the peanut butter jar lid, which I actually thought would be left out. Whereas for my water bottle, we actually had a lot more depth in our image than expected. And however, it's hard to tell, it's hard to determine the details of the water bottle, since it seems as though they have been lost due to the poor reconstruction of the normals due to the interreflectance within the water bottle. And we also played around with the epsilon values in order to get a smoother surface with epsilon values. And the epsilon is what we added to z when we were calculating the normals for integration, such that we weren't dividing by 0. And some future improvements that could be made to this project are using a darker background, since what we found is that some of the pixels within our target image were being mapped to the incorrect pixels within our reference image. And this is due to, a bit in part due to our thresholding, since our background and sphere intensities were actually a bit similar and hard to differentiate. And so that could help with this normal reconstruction. And furthermore, we could use a larger space when we're actually taking these photos such that we can replicate an orthographic camera better by moving the viewpoint and also the lighting further back as well. And yeah, these are some of the papers that I looked at, and thank you for listening.